Hello. Today, Divya, Alyssa, and I from the Adaptive Designs team will discuss the parametric modeling of the upper extremities. According to the Crash Injury Research Engineering Network, almost 25% of car accident injuries are upper extremity related, affecting the scapula, humerus, and clavicle bones. In automotive safety testing, finite element models simulating car accidents are time-consuming and expensive, causing the automotive industry to standardize crash test dummies to model the 50th percentile male body. Safety systems modeled after 50th percentile males jeopardize vehicle safety for other populations such as females, the obese, and the elderly. The adaptive design team addresses this problem by identifying correlations between bone geometry and human characteristics such as age, sex, stature, and BMI, creating parametric models representing bone morphology over a broad population. The upper extremities subteam studies the scapula, humerus, and clavicle bones while working alongside other subteams that research other major body regions, including the adult skull and the thoracic and cervical spines.
Our procedure for finding correlations between bone morphology and various human characteristics is visually represented in Figure 1. First, we research previous literature to analyze the limitations and strengths of prior research. Next, we receive CT scans from the University of Michigan Hospital and each subject's corresponding covariate data, including BMI, age, height, and sex. An example of the broad range of covariate data representing the humerus subject group is in Table 1. Segmentation is next. Using Mimics, a medical imaging software program, we segment each upper extremity bone to remove bone noise and smoothen the model. Figure 1 shows how segmentation allows each bone to be isolated from the body, characterized by the different colors of the humerus, clavicle, and scapula. Next, we landmark our segmented results. Landmarking allows us to turn our segmentations into scalable quantities to analyze and standardize. We place 21 landmarks on each humerus, 26 on each clavicle, and 24 on each scapula. This totals almost 2,000 landmarks placed this summer on the humerus subjects. The next step, mesh morphing, focuses on applying nodal correspondence between baseline and target models to transform the baseline mesh into the target geometry. This allows for the fine triangle mesh of the baseline model to be applied to each of the humerus subjects, known as the target models. The final step involves performing generalized Procrustes alignment, or GPA, principal component analysis, PCA, and linear regression to produce statistical models. GPA is an algorithm aligning each subject in the same coordinate plane. PCA identifies significant sources of variation in our multivariate dataset. Statistical analysis enables us to develop crash predictions for the upper extremity bones and run finite element model simulations.
Figures 2 through 5 highlight the several forms of results used to make conclusions about a population's upper extremity bone morphology variation. Figure 2 visualizes the results of the PCA statistical analysis performed on our clavicle data to identify the top 5 principal components of variation. Figure 3 is an animation of 10 random segmented scapulae, demonstrating the various shapes and sizes of the scapula over a population. Figure 4 shows examples of the predicted humerus models generated by varying age, BMI, sex, and stature. Lastly, Figure 5 also represents an error plot for age between the baseline and target models for the humerus data. In conclusion, past research has demonstrated an increased car accident injury and fatality risk for those outside the 50th percentile male population. The adaptive design team addresses the safety equity issue by developing parametric human modeling to represent a broader population. Our next steps as a team are to generate prediction models to fully understand the associations between the upper extremities bone morphology and the subject covariate data. With the advancement of self-driving vehicles, upper extremity-related injuries may become more prevalent with alterations in driver behavior and position. Understanding how the upper extremity bones vary in populations will help develop adaptive safety systems protecting all passengers. While it may be tough to do so, it is not impossible. Finally, we want to acknowledge and thank the faculty, the upper extremities team alumni, and the UMTRI and MDP programs for supporting us. Thank you for your time.